Hello everyone, I am Chamudi Fernando and I will be presenting our research on chest radiographs classification using multimodal deep learning, the comparative study. This research was conducted by Shyam Kolonne, Hashara Kumarasinghe, Dr. Dulani Nidhaniya and myself. I will start off with a brief introduction about the domain of our research. Lung diseases are a major cause of death around the world. Among these diseases, pneumonia, which falls under the acute respiratory disease category, takes a dominant place. The most popular methods of diagnosing pneumonia are chest X-rays and OCT images. COVID-19, which is found recently, can also lead to pneumonia conditions much severe than normal pneumonia. And also, they both can have somewhat identical symptoms. Both pneumonia and COVID-19 diseases can be diagnosed using chest X-rays. But for that, expert knowledge is crucial and the process can be time-consuming. Considering the severities of the two diseases, it is important to diagnosing and distinguishing between directly. As the contributions of this paper, we will introduce a deep learning-based approach to analyze chest X-ray images in an efficient manner. This approach will yield more accurate results in diagnosing as well as for accurately distinguishing between the two, which indeed will provide a verification for diagnosis through chest X-ray analysis. A number of works have been done to address this problem. Some of them focus on identifying one of the diseases, while others focus on identifying and differentiating both. These studies have employed widely used CNN architectures like ResNet 50, MobileNet V2, and VGG16. Most of the works have achieved either considerably high accuracies or high recall values. Next, I will walk you through the methodology that we followed. For the dataset, we made use of a combination of two datasets. Kaggle chest X-ray images dataset is used for pneumonia and pneuma chest X-ray images. For COVID-19 images, we used Kaggle COVID-19 radiography database. By testing on different ratios and analyzing the performance, we finalized the split ratio as 60% for training, 20% for validation, and 20% for testing. This is the workflow we followed. First, the input images will follow pre-processing and augmentation steps, then the training phase. To train models on the whole dataset, we estimate the model's performance by using 5-fold cross-validation. For the evaluation, we have used accuracy, precision, recall, and F1 score as evaluation metrics. Data pre-processing is performed to transform different images to consistent setting. All the images are resized to the same size and then normalized. Augmentation used on training set to generalize the images using width shift and height shift with a range of 0.1. We have implemented 4 models separately based on CNN architectures which are ResNet 50, MobileNet V2, Inception V3, and Xception. We have made modifications to the model architectures with these additional top layers: a global average pooling layer, dropout layer, and a dense layer. After experimenting with different combination of layers, we have chosen this set of top layers and added the same set for all 4 architectures since we are performing a comparative study. ResNet, as indicated in diagram, has an advantage over most other architectures due to its escape connections that prevent the gradients from vanishing in deep layers. The top layers that were mentioned previously are shown in the diagram. The added global average pooling layer sums out the spatial information by calculating the average value of each feature map of the output of the previous layer. Advantage is that there is no parameter to optimize in the global average pooling, thus overfitting is avoided. Since the dense layers tend to overfit and limit the ability to generalize the network, we have chosen a global average pooling layer over a dense layer. Then dropout layer is added to minimize overfitting. During the training phase, this layer randomly sets input units to 0 with a frequency of 20% rate. So these drop units no longer contribute in both forward and backward propagation. Then finally a dense layer as the output layer with softmax as the accretion function, since we are performing a multi-class classification. This diagram shows the used Untitled V3 architecture with the added top layers. There are two types of bottleneck layers in this architecture, as with and without skip connections. The bottleneck layers makes this architecture a lightweight model. This diagram shows the Inception V3 architecture with the additional layers. Inception V3 has used one-to-one convolution to reduce the number of parameters in the model. This diagram shows the Xception architecture with the added layers. Xception is an extreme version of Inception. It is based on depth-wise separable convolution layers with a residual connection that allows flexible modifications. We have carried out training using transfer learning, where the initial weights are set to pre-trained weights of ImageNet. All the layers are trained from the bottom, where the 4 modules are trained and tested separately. Moreover, we have conducted 5-fold cross-validation to assess the effectiveness of the model and to mitigate the overfitting. I shall now describe our choices for hyperparameters. As the optimizer, we have used RMSprop, which is a gradient-based optimizer, as it accompanies an adaptive learning rate. For the loss function, we have used categorical cross-entropy. And also, we have used learning rate reduction to get better convergence. Now I will walk you through the results of our study. We have used 5-fold cross-validation to assess each module separately. The average accuracy, recall, precision, and F1 score values are indicated in the table. We have focused on obtaining high values for both accuracy and recall, as it is crucial to identify as many positive cases as possible in the medical domain. While all modules have shown high performance, ResNet 50 has obtained the best results. MobileNet V2 has achieved the second best result. The accuracy and loss curves are shown for all 4 modules. All the modules start off with a lower validation accuracy and higher validation loss. After learning the features to some extent, the validation accuracy increases and the validation loss decreases significantly. Towards the end, the validation accuracy overlaps the training accuracy, while validation loss almost reaches the training loss. This indicates that all the modules perform well without overfitting. This can be due to the actions taken to generalize the modules, such as data augmentation and dropout. We have generated confusion matrices to visualize the evaluation, which allowed us to get direct comparison between true positives, true negatives, false positives, and false negatives. Compared to the existing studies, we were able to get comparatively higher performance. These studies were conducted for multi-class classification similar to our study. we were able to gain a high accuracy, precision, and F1 score, also a higher recall of 98.15%. Recall is an important metric in this sort of application as it indicates the model's ability to identify a person with the disease as positive. To conclude, our research focused on developing a framework for diagnosing pneumonia and COVID-19, which we did using MobileNet V2, ResNet 50, Inception V3, and Xception models with additional top layers. Since all the proposed models have shown promising results, this study can be extended to develop an ensemble model where the prediction of these models can be combined to minimize the generalization error and the variation in the predictions. Thank you.